Uncertainty and error. First we'll look at uncertainty. This is a measure of the limits of how far your measured value could be from the true value. This can be determined by the measuring instrument. For example, using a meter rule, it would not be reasonable to quote readings with an uncertainty of less than plus or minus half a millimeter. That is assuming you can decide whether a reading should go to the next line or the previous line. It's often safer to quote a reading to plus or minus 1 millimeter. This is because you need to decide the closest line at the beginning and end of the thing you're measuring. If you take several readings, you would get a spread of values. You'd generally quote the mean with an uncertainty of plus or minus half the spread, unless of course the uncertainty due to the measuring instrument, as mentioned above, is larger. If you're using a hand-operated stop clock, it's unreasonable to quote an uncertainty of better than plus or minus 0.1 of a second, even if the spread is less than this. It's usually more useful to quote percentage uncertainty, and percentage uncertainty is found from the absolute uncertainty divided by the quoted value multiplied by 100. I'll illustrate these points with an example. You use a stop clock to time a ball running down a ramp and obtain the following results. I've calculated the mean at 2.418 seconds. We cannot quote our answer to more significant figures than appear in the data, so we need to round the mean to 2.42 seconds. The uncertainty due to the clock is plus or minus 0.01 second, as it measures the times to 100th of a second. The spread of the readings is our largest reading, 2.45 seconds, minus the smallest reading, 2.38 seconds, giving a spread of 0.07 seconds. Half of this is 0.035 seconds, which I'll round up to 0.04 seconds, so we can give an uncertainty of plus or minus 0.04 seconds. However, in this case it was a hand-operated stop clock, so we will quote the answer as 2.4 plus or minus 0.1 seconds. The percentage uncertainty would be our uncertainty value, 0.01 seconds, over our quoted value of 2.4 seconds, multiplied by 100, giving a percentage uncertainty of plus or minus 4%. Now to look at systematic error. The word error tells us there's something wrong with the system we're using. A systematic error is where a fault in the apparatus or the technique leads to all the readings being too far in one direction. A simple example would be a meter rule with a damaged end, making all the readings too high. This we would call a zero error. Adding an ammeter that has significant resistance into a circuit would reduce the current in the entire circuit, and therefore we wouldn't be measuring the current that we wanted to measure. To reduce the effect of systematic error, take great care in designing your experiments, and if possible use two completely different methods to get your answer. I'm now going to illustrate the effects of random uncertainty and systematic error. If this is the true value of the property we're trying to measure, and we get results like this, this shows a large uncertainty as the results have a wide spread, but there's a small systematic error as the mean of these results will be very close to our true value. These results have the same wide spread, and so we still have a large uncertainty, but now they're all moved across to the right, showing a large systematic error as well. These results now have a small spread, so they have a small uncertainty, but they're still moved across to the right, showing a large systematic error. Finally, these results have a small spread, and so a small uncertainty, and would mean very close to the true value, showing a small systematic error.